Hi everyone, this is Tasaki. In this short video, I like to discuss the main results of my recent paper with Naoto Shiraishi. And I usually introduce Naoto as my young friend, but this time I feel like he's my advisor. You'll see why. Anyway, here we prove that the spin 1/2 XY and XYZ models on the 2 or higher dimensional hypercubic lattice do not possess any non-trivial local conserved quantities. I will explain this result. So anyway, let's get started from background. Mathematical studies of quantum many-body system can be roughly divided into two classes. In one class, you sort of try to solve specific models exactly by using these sophisticated techniques. And of course, this is a very rich field, and you get very detailed, precise information about the models. But this applies only to special models that are solvable or integrable. In the other approach, you try to prove general theorems that cover models in a certain class. But in this case, this class contains both integrable and non-integrable models. But there are properties or phenomena that are expected to take place only in non-integrable systems. The examples are like quantum chaos or the energy eigenstate thermalization hypothesis. But these approaches do not apply to this kind of phenomena because, first of all, this only applies to integrable system. And this is slightly better, but this kind of approach does not distinguish between integrable and non-integrable systems. So I think it would be fair to say that before 2019, there were essentially no mathematical result that exclusively applied to non-integrable systems. What happened in 2019? Well, to explain this, consider this model called spin 1/2 XYZ chain. Okay, so this is the Hamiltonian Jx, Jy, Jz, and H are real constants, and X, Y, these are Pauli matrices. Okay. And don't worry if you don't understand the notation. This is just an introduction. And it is known that this model becomes integrable when Jz equals 0. If you don't have this term, you can Jordan-Wigner this Hamiltonian into a free fermion Hamiltonian and exactly solve it. Okay, and because of this solvability or integrability, you find that the model has a bunch of local conserved quantities that commute with Hamiltonian, and they look like this. And these are too small to see, but these are translated sum of x z x y z y, or here this is a sum of x z z x and so on. And there are of course many. So you have q5, which is a translated sum of x z z z x and so on. Okay, so there are a bunch of local conserved quantities in this case, but this is a solvable case. And what Naoto proved in 2019 is that if these coupling constants are different, and if Jz is non-zero and H is non-zero, and then people believe that the model is non-integrable. And in this case, he proved that the model has no local conserved quantities with support size in this range. So you don't have to care about details. So, but he proved that there's no non-trivial local conserved quantities. Okay, so I think it would be fair to say that this, as far as I know, this was the first rigorous result that applied exclusively to non-integrable models. Okay. And this result of Naoto was extended to Ising model under magnetic field, the PXP model, and also by Naoto himself to the spin 1/2 chain with next nearest neighbor interaction, and very recently to the spin 1 model with bilinear biquadratic interaction. Let me say a few words about this work, this paper by Naoto. So this is a paper, and first of all, I want to stress that this was published in the Journal of Statistical Physics. I'm very happy about this because actually I'm one of the editors-in-chief of this journal, and it's open access. So you can read it for free. And this paper contains the proof for this next nearest neighbor interaction chain. But as you see in this appendix, it also contains pedagogical review of his Naoto's method applied to the prototypical case of spin 1/2 XYZ chain with a magnetic field. So if you're interested in this, please download this open access paper and read it. And actually I did. I read this paper very carefully with interest, and I was very much interested in, and I thought, extending this to higher dimension would be interesting, and I started working on this project with Naoto himself. Oh, by the way, this is Naoto, or I should say Professor Shiraishi. Okay, one frequently asked question to this result by Naoto and its extension is that do these results prove that the models are non-integrable? I would say that this is a bad question. Oh, no. I would say this may not be a good question. The answer depends on how you define integrability, of course. And one definition you can find in the literature is that the model is integrable if it has a bunch of local conserved quantities. So if you use this definition, the answer is yes. But anyway, the answer depends on how you define integrability. More important is what we find from these things. And one very interesting observation that we find for the moment is that a simple quantum spin model is either known to be integrable or does not possess local conserved quantities. This is an amazing observation. This means that, people who solve these exactly solvable models were really doing good job. And they found, I think, they found all the models that were solvable. Okay, so here, what we want to do here is to extend this kind of approach to a higher dimensional spin system into all higher dimensions. Okay, now let's move on. Let me move on to our main results. So I consider a spin 1/2 model in D dimension. First, I note that operators of a single spin is spanned by these four matrices, identity and the three Pauli matrices. Now I consider a spin system on lattice lambda, which is the D-dimensional L by L hypercubic lattice with periodic boundary condition. And by XU, YU, ZU, I denote the copies of these Pauli matrices at site U. And then this is our Hamiltonian of the XYZ model. We have this XX, YY, ZZ coupling for nearest neighbor sites and magnetic field. And these are just real constants. Okay? And we assume, this is the only assumption. We assume that both JX and JY are non-zero, right? And let me talk about local conserved quantities. First of all, by this boldface A, I denote a product of Pauli matrices. Okay, so AU is one of these Pauli matrices, and S, which is the support of this product, is simply a non-empty subset of the lattice. Okay, and so by P lambda, I denote the set of all products, and I define the width of this product as the maximum width of the support of this. Yes, this product. So when computing the support, so here we have, this is my A, and this is our two-dimensional lattice. And in this case, we have three operators, three Pauli matrices. But when looking at defining the width, we only concentrate on the span of this A. So here we have empty site, but you don't care. So to compute to determine the horizontal width, we count the number of sites at 1, 2, 3. Okay, 1, 2, 3. So I say that it has horizontal width 3, and the vertical width is 2 in this case. So you take the maximum, so this has width 3. Okay. Now a candidate of a local conserved quantity with this width, where Kmax in this range, is written like this. Okay. And so it's simply a linear combination of all these products here with arbitrary complex coefficient. And we make no assumptions like translation invariance or rotation invariance, no symmetry assumption about QA. They are just arbitrary. Okay. And this is general sum, but here is an important restriction. So we assume that here A is summed only over products whose width does not exceed Kmax. And we also assume that this is sort of saturated in the sense that QA is non-zero for at least one A with this width. Of course, this is a very natural assumption. Okay, so this is a candidate of a local conserved quantity with width Kmax. Okay, then this is very standard. We say that Q is a local conserved quantity if and only if it commutes with the Hamiltonian. Now we can state our main theorems. So these are all these, we already talked about this. Then our theorem says that there are no local conserved quantities Q with width K max in this range. Okay. And of course, you know that there is a local conserved quantity with K max equal to, that is the Hamiltonian. Okay? And here is a theorem about K max equal to conserved quantities. Any local conserved quantities with K max equal to is written like this. So it's essentially the Hamiltonian itself with plus some Q1, which is a linear combination of single site Pauli matrices like the total magnetization. So if you have conserved quantity like total magnetization, of course there is some ambiguity. And in some case you don't have this. Okay. But anyway, this is the most general statement that we can prove. All right. So these are statements that we proved. And let me say a few words about the proof. And so if you are interested in the details of the proof, then I have one more video, which is longer than 40 minutes. I'm sorry, but in which I explain the essence of the proof. Okay. Here I just very, very briefly talk about the strategy of the proof by using only 3 slides. Okay. So the strategy of the proof closely follows that developed by Naoto in 2019. And so this is our Hamiltonian, and this is a product. Okay, so since this is just a product of Pauli matrices, by using this table, you can easily compute. In principle, you can compute this commutator and write it as a linear combination of all these b's. Okay, and so this coefficient is of course expressed in terms of jx, jy, jz, hx, hy, and zz. Okay, you can just compute it. Okay, so this is our candidate of a local conserved quantity, and of course we are interested in this commutator. And now since we have this, the commutator can be written by using this like this. We have exchanged the order of sum, and so this is, the commutator can be written in this form, right? Now we require that this Q is a local conserved quantity. So this commutator is 0. And then this means that since these guys are linearly independent, each coefficient is 0. So what you find is that this thing is 0 for all b. So this means that we obtained a coupled linear equations for this QA. And then you can try solving these coupled equations by using your high school mathematics. And to find that in this case, the only solution is that QA equals 0 for all A. And then you are done. Your proof is done, and you found that there's no non-trivial local conserved quantities. But this is a very naive, very simple, very straightforward strategy, and I think it will be very hard to believe that this kind of simple strategy works in this kind of, non-trivial quantum many-body problem. And so very interestingly, back in 2019, Naoto found that this strategy with of course some very clever mathematical puzzle solving skill does prove the desired no-go theorem. So we follow this strategy. Okay, let's talk about some more details. So the proof consists of 2 steps, and like in Naoto's original proof. And the first step is rather easy and rather general. So this is, as I said, we have this coupled equations for QA and try to solve it. And first thing you find from this is if there is B such that this is non-zero only for 1A satisfying this condition, then then you don't have to sum. And this equation simply becomes this. And since this is non-zero, you can solve it, you find that QA must be 0. Very good. So in this lucky situation, you already know QA, and it's 0. And also, if there is B such that this is non-zero only for two A's, and then this equation becomes like this. And since both of them are non-zero, this can be written in this form. So these coefficients are related in this way. Okay? This is also very useful. And by using this basic relations and by using a procedure that I call the Shiraishi shift, we cannot use this terminology in our paper because it's it's a paper by Shiraishi and Tasaki. So we simply call it shift in our paper, but I call it the Shiraishi shift. So by using a very useful technique called the Shiraishi shift, by using these basic properties, we can prove this very important lemma. The lemma says that for any A with this maximum width, we have either QA equals 0, or QA is equal to some non-zero constant times the coefficient of something called ICXX, or QA is equal to non-zero constant times the coefficient Q of CYX. What is CXX? What are CXX and CYX? Well, they are sort of standard forms written here. Okay, and they are concrete concrete products. And one thing you first should notice is that x0 is some position and e1 is the unit vector in the one direction. So we are working in d-dimensional problem, but this is a product of Pauli operators, Pauli matrices aligned only in the one direction. Of course, there's nothing special about one direction. Okay, so without losing generality, we are looking at one. We are focusing on the one direction, and this works for any direction. But anyway, you can show that this is true. So this is not only special, but it's very special in the sense that it's all the operators matrices, Pauli matrices are aligned in one direction. Okay, and it has this form: x times z z z z z and x, and y times z z z z z x. Okay, and I think if you remember what I talked before, this is this standard form. Here you have x z z z x or y z. Anyway, so this is very similar to this form of local conserved quantities that you have seen in XY model. Okay, so these are just operators aligned in one direction, so that we can say that the problem reduced to that in essentially one dimension. And in the second step of the proof, we try to solve this one-dimensional puzzle. Okay, so what the strategy is very simple to say. So we have this coupled equations, and we still haven't used all of them. So you cleverly pick some B and write down some equations and try to solve them again by using your high school mathematics to show that the QCX and QCY are 0. Okay, and then by using this lemma, you see that QA equals 0 for any A with maximum width. But this contradicts with the existence of maximum width component, so we get our theorem. But I have to say that to accomplish this step, you have to solve some mathematical puzzle, and this puzzle solving is actually easier than the corresponding step in the one-dimensional problem that were solved by Naoto and in many works that extended Naoto's method. But it's easier than in one dimension because things get more non-solvable in higher dimension. But anyway, we still need some craftsmanship, and so I'm still looking for a better proof that it's more automatic. Okay, so that's all for the strategy of the proof, and let me finish this talk by summary and discussion. So here's a summary. We proved that the XY and XYZ models on the d-dimensional hypercubic lattice into a higher dimension possess no local conserved quantities. And in the simplest case, our theorem applies to the XX model with this very simple Hamiltonian. And in one dimension, this is very easily solvable. So this is exactly solvable model 101. Okay, but if you go to 2 or higher dimension, even this very simple model becomes non-solvable. And this justifies our intuition that quantum many-body models becomes less solvable in higher dimensions. And the strategy of the proof is a natural extension of that developed by Naoto in 2019 with some new ideas to treat higher dimensional models. Of course, we need some ideas. And discussion. I would like to say that the proof of the absence of local conserved quantities is interesting and meaningful by itself. Okay? It gives a strong indication that the models are not solvable, and it sheds light on the algebraic structure of quantum spin models. And after all, it's interesting. But having said that, I would also like to say that it is challenging to develop techniques for proving further results that are relevant, that are directly relevant to long-time dynamics of quantum many-body systems. One thing I want to try is to prove the absence of not only local conserved quantity, but quasi-local conserved quantities. A quasi-local conserved quantity is a conserved quantity which is a sort of infinite sum, but in which the coefficient sort of decays exponentially with the size of the support, so on. So it is known that some integrable models have quasi-local conserved quantities, and they play important roles in long-time dynamics. So I want to extend the proof of the absence of local conserved quantities to prove the absence of certain class of quasi-local conserved quantities. This is a very difficult question. And in the paper, we have very preliminary observation towards this direction. And much more exciting direction is to look for the relation between the lack of conserved quantities and something called the operator growth or the Krylov complexity. And this is more directly related to the long-time dynamics of spin systems. And more ambitious goal is to, in some sense, justify in some way the energy eigenstate thermalization hypothesis. But this is much more difficult because all these results dealt only with the operator algebra of the system. We didn't look at the states or the Hilbert space. But in order to go to ETH type question, we have to look at the quantum states or substates of Hilbert spaces. Okay, and there are many models which have like quantum many-body scar, which do not thermalize, while many other energy eigenstates thermalize. So if you want to consider ETH, you have to distinguish energy eigenstate which is a quantum scar or which are not quantum scar. So this is a very difficult question. And the current approach of looking at local conserved quantities do not distinguish between systems that possess quantum scars and which do not possess quantum scars. So this will be very difficult problem, but it's of course worth thinking about and worth challenging. Okay, so that's all what I wanted to say in this video. So thank you very much for watching. Goodbye.